Hello, good afternoon. I'm Hugh Dyer, an Associate Director in RSK's Geoscience business. Welcome to the second of our 2024 series of Down to Earth webinars. These talks cover a broad range of subjects through the year and are available afterwards on our YouTube channel alongside previous talks. Our talk today will be given by Dr. Paul Mahon from our geotechnical team, giving us a look at the economic design of ground improvement. This will be the first of our geotechnical talks this year, with two further talks scheduled for later in this year. Firstly, a brief note on housekeeping during the talk. All attendees' microphones are automatically muted throughout the webinar. During the presentation, you can post questions online, and please do, and there'll be a question and answer session at the end of the presentation. As many questions as possible will be answered during the webinar today. Those that can't be answered due to time constraints will be answered after the webinar by Paul. Shortly after the webinar, you'll receive a link to a short survey. If you could take a few minutes to provide feedback, please, so we can improve our future webinars, that'd be greatly appreciated. Now, please let me introduce our speaker today. Dr. Paul is a chartered civil engineer and a fellow of ICE. Paul is an associate director within RSK Geosciences and has over 23 years experience in civil engineering and contracting, house building and geotechnical consultancy. Following his PhD in cement stabilized limestone in 1985 with the University of Sunderland, Paul also has 25 years of academic experience as a senior geotechnical lecturer at the universities of both Bolton and Salford, and was operational lead at the University of Bolton prior to joining RSK in 2022. I'll hand over to Paul now to give us a run through the economic design of ground improvement. Thank you very much.
Thank you very much indeed, Hugh, and welcome to everybody online. Without further ado, I'll turn my camera off throughout the presentation and bring it back on again at the end. So as Hugh said, I've been around a long time, I guess is my description. Setting out engineer to begin with, and I would say that I've hopefully maintained a practical focus about life throughout all of my career, both in terms of consultancy and also in my academic life. I will be asking you to participate today, and therefore I've got a Slido questionnaire type thing. There's 3 questions, so if you would oblige me and just get a phone or device out and put slido.com and then that code number. When we get to the relevant questions, then there'll be less time delay, and just see from my perspective, it tells me a little bit about yourself as an audience. So without further ado, the content of the talk today has got several sort of subsections, and I'll be going through ground investigation foundation types with you, and then looking at aspects to do with the economic design, efficiency of design in particular, looking at the ground improvement considerations and techniques that are available, and then we'll be looking at a little bit at the direction we're heading in by way of looking at carbon costing solutions, and therefore a net zero approach, and then the Q&A at the end. So to set the ball rolling, if you could put the Slido code in on slido.com for me, and I'll just gain a little bit of an insight into what your backgrounds are. That's brilliant. Thanks very much. There's more than 100 on the call today, so I think I'll settle at about 58 and proceed. But thanks very much. So, consultant background, there are developers, contractors, no unemployed, retired, or students present, and some regulators. That's good. So ground investigation and foundation types to begin with. Way back in time, Site Investigation Steering Group made a statement regarding quality, risks and safety in site investigations, and the statement that was made was, you pay for site investigation whether you do it or not. I think that message has been repeated many, many times, and therefore that statement probably still applies today. So a low-cost site investigation may be low cost initially, but longer term you may pay for it, is the message. I guess you might hit lucky and that not be true, but if you hit unlucky, then there could be consequences. Published research suggests that if you spend around about 1 or 2% of the project value on the investigation stage and the planning, then you may still result in project costs escalating to in excess of 50% beyond project value. And primarily those tend to be ground related issues. By doubling that budget, the research suggests that your risk then drops to only 5% overrun on costs. Now that's published domain, it's not me making the numbers up. Moving on to what the section headings in the Site Investigation Steering Groups have been over the years, and these still apply today, although there are updates from 1993, but the point I'm making is it's been around for a long time, this thought process. What we're talking about really is, risks in the ground, effective investigation, specifying it well, and making sure above all else that all works on sites are safe. Ultimately, what we're trying to do with project design is we're trying to eliminate risk as much as we can, and therefore determining a ground model in the same way as for contaminated land, a conceptual site model is derived. We have a similar thing for the geotechnical side, and realistically those models should work hand in hand. So there are environmental consequences to geotechnical issues and vice versa. So we're really trying to determine what soil's there, how uniform is it, what's its strength, what's its deformation characteristics, how is it going to behave, and then can we model it well? Is the groundwater mobile? Will that cause us difficulty during on-site excavations? Will that cause a strength reduction? Is it going to be difficult to control it? Will the groundwater have contaminants within it? There's lots of issues and questions come out of this. And an effective site investigation will aim to try to reduce that level of uncertainty as much as we can in a phased manner. So not necessarily all in one go, but primarily a snapshot, if you like to say, to give an idea as a first stage, and then that gives a bit more confidence in the overall geological picture. With that in mind, the standard way in which investigations are carried out would be using a desk study approach and then site works. The desk study would primarily be your archive searching. We're pretty lucky really in that the geological maps and previous history and experience amongst consultancies will tell us what we're expecting. Aerial photographs, ordnance survey maps, historical information, lots of sort of archived information will give us greater confidence. The site works themselves, you might argue that the walkover could take place as part of the desk study. But if it didn't, then certainly before the site works start, you're definitely going to be doing walkovers to check access, etc. And then the non-intrusive techniques can indeed be utilised. There was a talk in January by Charlotte Usher on geophysical techniques, and some of those techniques are really, really useful with certain site geological conditions, so it's something just to be aware of, and it's one of the tools in our toolbox. And then we get to the intrusive stage where we're trying to get sort of quality in situ data. We're looking at visual assessments, we're looking at large volumes of soil, we're looking at small discrete samples, we're doing sophisticated tests on those in the laboratory. We're trying to come up with our sort of methodology for predicting what's going to happen on site. So all of that is taking place on every site investigation, whether you're looking at a site where the ground conditions lend themselves to ground improvement, or whether they are just looking at traditional foundation. That in mind, I suppose the cheapest situation on site for us would be we get to site, we do our investigation, we find competent materials within a very sort of shallow depth so that we can use traditional foundations near to surface, and they conceivably going to be the cheapest things that we're going to get away with. It's not necessarily get away with, but it's certainly if the ground conditions are adequate near to surface and we don't have, say, trees and desiccation issues with clays, then that shallow foundation may be absolutely fine for the purpose. What we'll be doing throughout this exercise is looking at the depth into the ground the foundation needs to go and how wide it needs to be, or what its breadth is, so breadth B. And we'll be using our interpretation of the ground profile below certain depths in the ground to determine at which economic depth should we place this foundation. And then we'll come up with options and we'll cost them. And then with communication with clients, we can come up with an optimum procedure to follow for that particular site and that particular series of loads and deformation requirements for that particular structure or engineering feature. What we're really doing is trying to work out what load can this soil take to an acceptable settlement, or we might need to go for something different, which might be a wide raft foundation, deeper trench fill, or piled foundations. And if we think about it, if we've got a strip footing in the ground relatively near to surface, then what we've got is a load being applied to the soil. So it's a line load around maybe the perimeter of a building, if that's brickwork. And there's a zone of influence, there's a pressure bulb below that foundation, which is stressed by the load applied. And it's trying to assess how will that ground within the zone of influence of the foundation perform, both in terms of its shear capacity and the deformation that will take place, both in the short term and over a longer period of time, depending on the soil type. Likewise with the pad foundation, which might be an isolated column load from a structure, so a structural frame building in a warehouse, for example. And again, due to the load on that, there will be, for the geometry of the foundation, a certain pressure bulb for that foundation as well. And then we connect the ground between these load application points with floors. We need floors. Ideally, a ground bearing slab will be the cheapest form of floor that we could probably get. And the issue here, just to bear in mind, is that because the floor slab is over a wide area, then the zone of influence extends down a long way. So even though the stress is relatively small, it could generate a significant volume of soil stressed to that small value, and that could generate a movement of that floor slab. We might need to look at suspended floors. If we did that, then all of that floor slab weight would have to go to the perimeter loading applications, and then those loads would be higher. So it becomes very, very difficult to do that. Or we might look at ground improvements underneath where the floors are going to go. And it could well be that due to assessment of the differential movement between what we think the foundations are going to move and what the floor slabs are predicted to move, if that differential is excessive, then we would use ground improvement to attempt to take out the settlement within that floor slab area. At this stage, I'm going to ask another Slido question. So in terms of your coverage of foundations, what foundations from that list have you experience of, just for my own personal interest? Thank you for that. That's really interesting. Significantly, everybody pretty much knows pad strip foundations. Have probably used them. Raft foundations, second in the list, and then we've gone into sort of piling techniques, and concrete probably slightly ahead of steel. And then we do have ground screws, screw piles, which primarily are coming into fashion, if you like, with requirements for tensile capacity or uplift capacity. where light structures may need to be bedded down into the soil, but not very many people have been familiar with using those. Thank you. So moving on to economic design. I'm not going to put pounds and pence here. I'm talking about economies by way of the techniques and the way in which we go about the thinking about the ground improvement solution. So in terms of economic ground improvement design, then economic, if you look at definitions of it, it's associated usually with a production line, about making something, goods and services, but it's not always the case with us. I would say that its efficiency of our cost and approach is probably the economic part of the economic ground improvement design. And then when we're doing the ground improvement, it's the technique, and again, it's the efficiency of it. I think the common factor here is the efficiency. Are we looking for a short-term cost savings or cheapest foundation solution? May well be fine. Will that give any long-term consequences? Will that particular solution be harder to decommission and to reuse the sites? Will that be harder on carbon costing? So is it a short-term cost saving but might give us a longer-term issue or problem just to think about? So that's what I'm saying here, really, that to some extent, are we beginning to move towards looking at long-term reputation on schemes and looking at value added at the end of the period, looking at the maintenance of the structure and looking at ability to increase the structural capacity of the building? So can we put 2 more floors on it, for example? So could we change the use of the building easier? So is that worth considering at that design stage? Not always the case. Then final question from me, just as I'm moving into ground improvement techniques, I'm just intrigued to know which of those have you come across, and would you rank them in order of your, if you like, preference for using on sites? So the ones that you personally used, which of them would you prefer to use? Thanks. This is really interesting, this, because I'm seeing a changing picture depending on people's experiences. Yeah, it's a pretty equal spread, really. At one stage, excavate, recompact was at the bottom of that list, and it's now at the top. So I'm sure we could continue with this exercise for longer, but thanks. That just gives me the snapshot that I was looking for. So moving on to ground improvement considerations. So all engineering to some extent will change the ground, and therefore there will be things we may wish to do to the ground. And in the Syria report, it's a bit of an old document, but I think the principles still apply today. So in ground conditions that are regarded as poor, however you define poor, they're regarded as 5 options. So bypass it and take the foundations deeper, and then they don't have to rely on the support capacity of the near to ground surface, but you will have to suspend floors to perimeter loading, which makes them become bigger, so power loads become higher. Remove it and replace better material. Again, that was quite fashionable a long time ago, where we had available material that was easy to put in its place, but now with transportation costs and what you're going to do with the material you're removing from site, it isn't really such a good idea. So we're going to probably want to keep it on site, and we want to try and improve it, and therefore the ground improvement techniques come to bear in mind. Are we going to design the structure to basically not put loading on it and therefore bypass it in that way? Are we going to treat the ground, which is subjective today? And I guess the 5th option, that was a bit of a strange one in my eyes, but it's what was published, was to abandon the project entirely and look at a different site, which to me seems to be that if you've got a difficult site, you ignore it and go for a greenfield site, which isn't good environmentally. So there's a lot of thoughts in my mind about all of those 5. Then moving on to a definition, I'll just let you read that. So it's quite an interesting thing, this, that the ground is what it is, and if we need to use it, then we may have to change it. So we've got quite a powerful responsibility in life here to try and come up with a way of using this soil rather than just throwing it away and bringing in more material from somewhere else. And the comprehensive range of approaches that Syria 572 and 573 published is a big list of things here, which primarily talks about agitating the soil or adding load. Now, what we're talking about here is the soil type. So if we've got a primarily granular material like sands and gravels, all right, with a cohesive fraction, so with clays and silts in them, but primarily granular, then applying a physical energy, a vibration, a compaction activity will densify the soil, reduce its void space, and make it less prone to settlement under final building structural loads. If we add load to the ground in some way, then that load added will make that granular deposit sort of settle. It might not be an efficient way of doing it, but it is a way of doing it. So if you've got enough time to wait, you can put a surcharge embankment in place, and then it will generate a settlement over a relatively short period of time if it's granular. But if it's clay material, then it would be over a longer period of time. Then going through the rest of the list, there's structure reinforcement fill. You can all read the headings yourself. These are all ways of trying to maybe fill the void space, put reinforcement between soil particles, filling in completely with grouting using admixtures, very expensive. Thermal stabilization using heat treatment to form vitrified sort of boundaries, which is a very expensive way of going unless electricity is very cheap. Using vegetation and natural solutions. So all of those in combinations are used on sites. Just to kind of whiz through each of those subheadings, so looking at vibration, then vibrocompaction, fibrostone columns, dynamic compaction, again, you can read the things there. The one on the bottom of the list is a bit, well, crazy, I suppose, blasting. I don't know if anybody's ever put explosives in the ground and tried to blast the soil to make it densify, but it was used originally in the United States. I don't think it's primarily used in the UK. So some of these techniques might not be ever used, but some of them are used quite a lot. So the vibratory techniques are listed there. Adding load, well, pre-compression, vertical drains, inundation, flooding, vacuum preloading. So as well as the surcharging, we can put tubes in the ground and apply a vacuum, and that helps by generate a suction to take the water out of the pore space to accelerate the consolidation of surcharging activities. Dewatering and use of pressure berms could all be applied. Structure reinforcement, again, you can just read through those. I'm not going to read them all out because of the space I've got available today, but I'm just trying to show there's a huge range of techniques can be used. Structural fills, admixtures, including the stabilizations using lime and cement. Grouting techniques, both in terms of permeation grouting, compaction, compensation grouting, and then thermal stabilization, as well as ground heating. You can use ground freezing, but that might be to demobilize groundwater inflow into excavation trenches. One final technique by way of sort of vegetation is to try and gel everything together, shall we say. Again, some risks to be overcome. Settlement is the primary one. Consolidation, time-dependent movement, and differential. The next lists are risks, but not necessarily geotechnical, so I'll skim through these relatively quickly. You can all read them as they're appearing. Groundwater change is very topical in terms of climate change, and how groundwater moves might affect slope stability and might affect foundation capacity of large loaded structures in built-up city centre areas. So that could be something to have your eye on for the future. And ultimately, all of these works are going to be carried out in a safe manner. So health and safety is absolutely crucial. The most important or the most common methods used, in my opinion, your earthworks, your compaction, your addition of cements, and these can be used on either granular or cohesive soils. Your vibrocompaction, the word compaction is really telling you it's a granular material. Stone columns, or sometimes called vibro replacement, is form a hole and replace it with stone. And primarily you're going to use that cohesive material, but it can be used on granular. But in a way, where you're removing granular material out of a hole to then fill it with granular material again is a little bit strange. But ground improvement can be adopted, and there might be reasons why you want to do that. But if you've got granular already, then densify it and use vibrocompaction. Vibroconcrete columns are where the soil itself doesn't have enough lateral supports, and therefore the column might not remain stable. So instead of that, you would use a vibroconcrete column that's getting a bit close to piling, but is nevertheless used. And then using surcharging with band drains on a cohesive material that's got a low strength. I think the point about this is that all of these soils will be poor soils, otherwise you wouldn't ground improve them. Specialist ground improvement contractors have got a variety of techniques. They're developing suggestions and deviations on techniques all the time. So they're well worthwhile being familiar with the full range that are currently being put onto the marketplace. And in terms of the granular soils, they are primarily either very loose or cohesive, very soft or organic materials. Compaction, again, I'm going to whiz through these relatively quickly. Standard compaction testing on soils from investigations will show you the relationship between the moisture variation on a soil, and there'll be a peak value that's the optimum moisture content, which will tell you what the theoretical maximum you're going to get for idealized compaction, and that'll give us, say, 4% void space, which is 96% compactive situation. So you change your specifications for earthworks, then you can use these curves to decide whether you're going to get there or not. And what you'll notice is that as the sort of clay, as the granular content of the soil increases, the optimum moisture content will reduce, and you need to be aware of that. Likewise, energy-wise, the energy profile of that increases, the optimum moisture content will also change. So geotechnical people will look at the data you get from site investigation, come up with recommendations on, is the moisture appropriate for use. Compaction, we're going to increase density, increase strength, reduce permeability, and indeed that gives us less settlement overall. We might need to add cement or lime. If the moisture is too high, adding cement or lime will reduce the moisture within the soil if you give it a few hours and you mix it in, and then you end up with the ideal conditions for compaction. Environmental and geotechnical excavations on site may end up looking like that, which has got a lot of visual there in terms of obstructions and a lot of water to deal with, and you can see it's a complicated mix. Vibrocompaction on site is poker in the ground, apply a lot of vertical and lateral energy and try and densify the soil around the sides of the poker installation. Stone columns are basically form the hole and fill it with gravel. And then concrete columns, the vibroconcrete columns will form the hole and fill it with concrete. Surcharging is apply a embankment of soil above your required final level, and then that increased height is adding extra weight that will help the soil to consolidate. And what's really going on here is we've got weight. The water pressure is a clay soil. It's a low permeability, very soft or soft clay soil, which will settle a lot over time, and therefore will generate a poor water pressure if we apply some load to it. And what we need to do with that is we need to somehow apply vertical drains in the soil and make that water within the clay void space get to the drain, and it'll get there by going laterally and then vertically. And if it's going vertically, there's an equation there that simply says the distance it has to travel, the d, in that term for time is squared. So there's a very huge time delay if that distance becomes bigger. If you go for the radial situation, the radial direction, if it's flowing to a vertical drain, it's got a much shorter distance to travel, so the time becomes much smaller, is what I want to say on that. An example of a site that I looked at quite a few years ago is a 25-meter deep infill sand pit. We built a trial embankment on this site. We then built the full scale on the residential development. What you can see here is some houses already being built. They are instrumented. You can see compaction control taking place here. We had phase one imported in one amount of material to site, so sand from a local quarry came into site, 6 meter high. After its satisfactory settlement of the clay pit took place, we then moved the upper 4 meters into phase two, and then started building the houses on the phase one. And then the next stage was to go to phase three to move the upper 4 meters from phase two to phase three. And then finally, after that, the amount of material left was calculated to then stabilize the gold clay slope. And that was a perfectly engineered job that basically is a site that was worth very small amount of money. £350,000 was the purchase price. £700,000 of investigation and remediation costs brought it in as a £6 million value site at the end of about a year of investigation. Moving on, here's a hydraulic sand placement underground in the northeast of England in a fire clay mine. Huge void space, very expensive, would not be able to make that a viable site by just filling it with PFA cement grout. So instead of that, put boreholes in. You can see sand hopper, you can see a sand conveyor, a water jet hopper, borehole, 8-inch hole, 200mm diameter hole down, intersecting the void spaces. That's me in there sampling the sand. That's a half built cavity now. We've got it to go within about 50mm, 100mm of the roof from a very limited number of injection points. And then we fill that upper void space with PFA cement grout. There's a lot of guidance around with NHBC, primarily for obviously developments, giving lots of sort of, well, standards to refer to, I guess. So you can look at those at your leisure. There's also guidelines on the way in which soil types can be treated by different techniques, and there's lots of these type of guidance charts that one can look at. Ground improvement contractors, etc., have lots of these charts available. Moving on very swiftly, because I'm conscious of time and I don't want to overrun by much. Net zero ground improvements. Wow, that's a very busy slide that you can't all read. 100% know that, but we're basically trying to itemize everything you do on a site from the beginning, from the cradle to the end, to the grave and beyond, to the future life of the project, so that we're trying to itemize what's happening on this site from a ground investigation perspective, and from a ground improvement perspective, and from an engineering perspective, and how can we sort of cost that? How can we look at maybe the carbon efficiency of it, because that seems to be the direction that we're heading in with a lot of these things now. Keller's in particular have published, and it's easily available in public domain, all of this, the way in which on their projects they are looking at carbon costing all of their activities, because you then can compare one against the other. Within RSK, in conjunction with Leap Environmental, we're also looking at using a system we're calling credits, so that we're using credit foundations, credit earthworks, and we're rolling this out across the business currently. And then just to kind of look at a slide there that's from Keller again, and it's just showing there that the materials usage in terms of the carbon costing of the foundation activities seems to be a significant portion of their overall activities. But by analysing it, people are building this data bank up now of the way in which they can economise and come up with an economic foundation solution. Final comments from me. Ultimately, you need to know your soil type. If you've got a clay, then you load it. The water in the void space of clay will not move quickly, and therefore you have to know that. And if it's a poor quality soil, it will reduce in its void space and it will settle. And it's trying to predict how long will that take. Obstructions in the ground are crucial as well with ground investigations and ground improvement techniques, because obstructions will cause big problems for your site ground improvement techniques. Another sort of properties and details, so we're looking for their strength, variability, and also what's their extent both vertically into the ground and laterally, so how variable are they? And unless we have enough investigation there, we may not know that picture accurately, and therefore we might be being a bit economic on the too conservative side with our design recommendations until we have enough confidence that we can give a more accurate picture, which will then bring down the costs of the schemes. So this is all about defining the ground model with certainty. Is 85% certain good enough? Well, we all want 100%, but we're talking about ground here, so there will be things that are a bit different to what you expect, and it's up to us to try and make sure there's no hidden surprises. Understanding the loads at the very beginning, so knowing what is required on the site, it's just crucial really to then design the investigation appropriately and to make sure the right ground improvement techniques are put forward, particularly settlement requirements, not just the loading, but how is it going to move. So this is really then allowing us to define the range of ground improvement options. We can then look at sustainability, etc. We can look at program implications, because one technique might be technically great, but then another one might give a time efficiency. So whilst it might be a little bit more expensive, it might be better on time, and therefore you might want to use that approach. And this is all by mutual communicative agreement with clients, really, so that understanding client needs is crucial to all of that. And I think that then, of course, brings us into the final cost of the scheme, and then we make a decision and we go ahead with it. And that is a whistle-stop tour of ground improvements. And we now get to the question time.
Thank you, Paul. That was a very, very good whistle-stop tour through the subject. Thank you for that excellent talk, and some very good points to bear in mind there. So we have a number of questions now coming through the portal. Anyone who wants to submit their questions, get them in quick while we're going through this. So first question, which comes from right at the start of your presentation. When we're talking about the spend in foundations, whether you do the site investigation or not, when you talk about project costs, is that the project overall costs or the foundation costs that are influenced by the site investigation?
No, that's a really good question. My interpretation of it has always been it is the total project cost, but I do understand that that's a big number. So it's a bit like, but then it's a bit like the, you're calling, if it's just the foundation costs, then they could be relatively small, and therefore the amount of money you're going to spend, if you use this 1% or 2% figure, I think that the whole point I was trying to make with that particular slide is that it's known that perhaps people are a bit sort of on the cheap side, I suppose. Sometimes it's a bad word to use, but people maybe are looking for penny pinching is not a good phrase either. But it's, a low cost investigation is going to give you potential problems. That's the point I'm trying to make. Whether the 1% is of the total foundation cost or the total project, I'd have to check exactly what they wanted to say in that report, to be honest. I always thought it was the total project value, but I'd stand corrected if somebody's going to disagree with that.
I think a follow-up to that question was, do you think that there's a difference in that percentage cost for greenfield and brownfield sites?
That's a good question as well. If you've got a greenfield that's in a historical, geological, competent soil area, then the foundation is going to be relatively straightforward, so that the uniformity of a site, so if I was talking southeast, talking London clay site, I'd expect it to have certain behavior. if I'm talking about a site where there's an industrial past, which is obviously the brownfield site, then it's very, very different. But if I was talking about Formby or East Anglia, then we know that the ground conditions there are going to be difficult. So that it's a green field, but is it a green field with soil that's competent or a green field with problem soils? So it does depend really as to how you interpret that, I'm afraid. I'd say the same as well with brownfield, because it could be a brownfield on competent materials, or it could be a brownfield that had a lot of previous investigation and remediation prior to development as well. So I don't think there's an easy answer to that question.
No, I think you're right there. Is it important to have a close relationship between the structural and civil designers and the geotechnical teams to help with maximising the efficiency of the ground improvement?
I'd say 100% agree with that. 100%. It's actually working with the structural designers intimately, I suppose, that we need that soil structure interaction has been an age-old issue, really, that I think you can go down the route of modeling and you can use computer programming, but I think the old-fashioned talking to structural people who deal with these sorts of projects, they know the client requirements, they understand, you know, what they need. I think the geotechnical team sometimes get enormous benefit by talking early doors to that structural team. And it doesn't cost very much by way of time because it's just a few conversations. So I 100% agree with that. I've always liked to work with structural designers, no matter what sector I work in, energy sector or developments or warehousing, commercial retail, whatever it is. I've always found that if you get that chance to speak early, it brings a huge economy into the entire process.
I tend to agree there. Yeah, absolutely. Next question. What about dynamic compaction and rapid impact compaction?
Yeah, that's a good point. I mean, you might say it's a form of sort of compaction, densification, vibration. I didn't include it on the list. I know it is used in former estuary areas in particular, where you don't have built up other structures and services maybe in the ground to worry about. But 100% using dynamic compaction or rapid impact compaction would be appropriate for certain site situations without any doubt, and relatively efficient and have significant zones of influence, I suppose, as well. It does depend on the treatment depth that you've got to try and improve as to which technique would be most effective for that site. So again, 100, yeah, I agree.
I've got a question here. What sorts of change in design and material should be made on sustainable methods such as geopolymers and biobinders to make them as budget ground improvement methods?
If I'm reading that question right, I'm thinking, are we exploring, should we be using plastics at all within geotechnical improvement? Am I reading that right, or?
Yeah, so our geopolymers and the use of geopolymers and biobinders budget or economical ground improvement?
No, I hear what Simeon said. If the use of a geotextile sheet can mean a piling platform doesn't need to be 1.2 metre thick, but can be 600 thick instead, you might argue that's halved your requirement for the importation of gravel. There is a potential, what shall I do with my geotextile? I'm advocating use of plastics in a carbon kind of thought process world. There are a lot of organisations currently looking at biodegradable geotextiles that might give that short-term fix that will then degrade naturally. I think there's a lot of companies involved in those areas are definitely looking at that as a way that they can stay in business, I suppose, and also help the geotechnical capability of schemes.
Okay, hopefully that's what that's covered that one. Looking at the infilled sand pit, given there were high walls encountered, how was that overcome?
Okay. I mean, basically, that site had a lot of investigation carried out, including probing on a 1 meter spacing, about 25 trial trenches around the perimeter to trace down the high wall, aerial photographs that were sort of stereoscopic aerial photographs from flypasts. So we had a contour diagram, and then we were trying to prove where the high walls were. And there became a no-build zone, so that on the development plans, we produced a zone where anything that was within a certain depth range, I can't remember the numbers now off the top of my head, but 1.5, 2 meters down to about 4 meters. If it's deeper than 5 meters as a high wall, it won't make any difference to the ground behavior. So we did a lot of work there to try and pinpoint where they were, and we needed to be confident about it. And so pretty sure that we were confident. And also the other thing I didn't mention, I think I said instrumentation, but the shore houses were instrumented with magnetic extensometers through the middle of each plot. So the first 4 show houses were fully instrumented. And then pressure pads below the reinforced concrete slab foundations, precise leveling, all the normal really. And I think from memory, the surcharging gave settlement to perhaps 500, 600 millimeters in the center of the pit. When we did the individual surcharge embankments as a trial, we only had about 400 millimeters of movement. So we knew the numbers and we knew the settlement time relationship, and the material within there was primarily a granular material. So we knew that once it had settled, that's it, further settlement would be arrested. But we did have long-term monitoring on that scheme. It did end up published in the IC Thomas Telford publication. That I could probably get the reference if anybody wanted it.
Okay, that's really good. We'll end the questions there, and any further questions that come through will be answered once Paul's had a chance to review them. So thank you again to Paul for a fantastic presentation and excellent answered questions. Our next Down to Earth talk will be on Tuesday, the 12th of March, focusing on sustainable soils and the challenge of achieving sustainable development through redevelopment. Please remember to complete the feedback following the presentation, and thank you ever so much for attending today, and we'll see you again in March. Thank you very much.